My name is Louis Daniault. I'm currently working at PCO, at the PCO group. I'm very glad to be invited to present to you the last results we had, especially in Salle Noire 2 and Salle Noire 3. So just for a quick recall, we have in Salle Noire 2 quite a nice laser as a daily driver. So it needs to be reliable and stable and to be used every day. So that's why we just wanted to keep that in as much as we can, to keep it efficient and for daily use. So we have experiments in Salle Noire 2 with the solid target, for instance, for harmonic generation and attosecond science. And we also can send the beam to Salle Orange, where Appli can work with our laser. And also we have Salle Noire 3, in which we play around, let's say. And so we can make lots of developments, especially developing and designing new stages that could be sufficiently reliable and stable so that we can transfer them to Salle Noire 2. And so we do that for amplifiers, for instance, for amplification stages. But today I'm going to talk about what involves nonlinear processes. So we have two main topics. The first is post-compression, which is made for just shrinking the pulse duration down to the few or even single cycle pulses regime, and the temporal contrast cleaning, which is to get the nicest pulse possible for matter-laser interaction. So, well, this is the outline. So we start just with the temporal compression. Just going to show you how it works and what's that for. What is the current setup we have in Salle Noire 2 and how we can improve that using a new design, which is based on a multipath cell, what we call the MPC, and the results we had in Salle Noire 3. And then we have another nonlinear process which helps us to temporally clean the pulses. And so we can do so with two different ways. The first one being what we call nonlinear ellipse rotation, NER, and the other one is cross-polarized wave generation. So we have an XPW setup in Salle Noire 2. There is one in Salle Jaune as well. And so I'm going to show you what we did in Salle Noire 3 to improve the efficiency and the reliability of those techniques. So I'm going to start just with post-compression, so you can call it whatever you want. And it's mainly temporal compression, that is making the pulse as short as possible out of the laser line. So the goal is to reach the few cycle regime or even the single cycle regime, that is just one electric field oscillation within the pulse envelope. So this is this kind of shape you see top right. And we have two advantages for that. The first is that we can drastically increase the peak power of the pulse if we can preserve the nice energy, but by just decreasing the pulse duration, we drastically increase the peak intensity and also the interaction. And also because we can trigger phase-sensitive processes. For instance, we can talk about the talk given by Luca a few months ago about the electron beam deviation with respect to the carrier envelope phase of the pulse. We can also talk about, I'm going to stop with that. We're going to also talk about go away. The generation of isolated attosecond pulses. So we here on the right, continuous high harmonic generation spectrum. So it means that we have one single attosecond pulse, and this is only possible with nearly single cycle pulses and with the control of the carrier envelope phase. So there are also many others advantages for time-resolved experiments, for instance. But the problem is that we don't have such short pulses out of the amplifiers. So for TISAF systems, for instance, it's about 30 femtosecond second. And for higher average powers, just like ytterbium-based laser systems, it's more like few hundreds or even 1 picosecond. So that's why we definitely need to add an additional stage at the end of the chain, such that we can decrease the pulse duration down to the few or single cycle regime. So I know that maybe most of you know how it works, but I'm just going to recall the basics for that. So for the pulse shortening, we need to broaden the spectrum of the pulse And for that, we use the Kerr effect, which is a third-order nonlinear effect. And especially, it's a self-phase match, because we have a star here in one of the E of the electric fields, which means that you can experience the Kerr effect in any kind of material, provided that you have sufficient efficiency. And so often you want to avoid that, especially in the amplifiers, because it can destroy the pulses. But when the pulse is Fourier transform limited, you can take benefit of it. So you can describe this quite easily. So the nonlinear polarization, you send it through the Maxwell's equation and so on. And it appears that you can consider that the beam is propagating with a nonlinear refractive index, which is dependent on its intensity. So it means that if you start with a Fourier transform limited pulse here with a flat phase, then if you experiment XPM, you get a nonlinear phase which has the same shape of the pulse, because it's proportional to its intensity. And you can characterize this nonlinear effect, the strength of the nonlinear effect, by what we call the B integral, which is the maximum phase at the top of the pulse. And this is proportional to the N2, the nonlinear refractive index, or the chi3 of the nonlinear process. So it depends on the material, the peak intensity, and the propagation length, because it's a cumulative effect. And so how does it work? Actually, if you derive this nonlinear phase, you can access to the spectral content within the pulse. That is what we call the instantaneous frequency. And so you can see that we have a linear chirp. So the chirp is linear, but it's a nonlinear process, but it's a linear slope, let's say, and the highest B integral, the higher slope. And, but the pulse didn't change its shape. It's still the same duration, but now it's not Fourier transform limited anymore, it's chirp. So it means that we could access much shorter pulse duration by compressing this nonlinear chirp. So indeed, we created new frequencies, and we can characterize the spectral broadening by the B integral. Actually, the B integral is directly the broadening factor, or I mean coarsely, the broadening factor of the spectrum, and so the compression ratio of the pulse. So if you have 30 femtosecond, with the B integral of 10, you have 3 femtosecond in the end, if everything goes well, of course. The problem is that this effect is also spatial, because the intensity can be described in time, but also in space. So if you do that with, let's say, a collimated beam here, so you have a Gaussian beam with a flat spatial phase, well, you have the exact same effect. It means that you have a Gaussian spatial phase. So at first order, it's a parabola, so it's going to focus the beam. So that's why we call it self-focusing, just like self-phase modulation. Here we have a focusing effect. And this is only the first order, because the higher orders will induce aberrations, modulations, and so destroy the beam profile. So if you look at the far field, then you have many features all around, and so you destroy the beam profile. So it means that you cannot get a large spectral broadening without destroying your beam. So we need to get rid of that, and the worst case, I mean, this is the regular case, but the worst thing is that when you mix time and space and consider the whole beam and the whole spectrum, well, for instance, here you can see a beam which will propagate through a nonlinear medium with a homogeneous spectral content all over the beam. And if you go through this plate, well, the highest spectral broadening will occur at the center of the beam, where the intensity is maximum, whereas at the edges, almost nothing occurs, and it's just a linear propagation. So now you don't really know what's the pulse duration or what's the spectral content of that beam, because it's different everywhere. So it's what we call spatial spectral couplings, or inhomogeneities, and well, in the far field, I guess that you will get some surprises. So we really want to avoid that. So you want to keep the temporal effects and just get rid of the spatial effects. To do so, well, it's been 26 years now that we can use hollow core fiber. So we just send the beam into a fiber, a guiding structure, and first it provides really nice beam qualities because of the guiding effect, but also it mixes the rays, let's say it's naively, it mixes the rays and blurs all the effects, such that the overall outcome is that the beam has an homogeneous spectrum, and that way you can get rid of the spatial effects and have quite huge spectral bonding with this. So what you do is to use hollow core fiber, so you can get higher energies, and fill with gas, usually noble gas, at any pressure to tune the nonlinearity. And as the beam is quite small and preserved over long distances, you can have small, rather small footprints for the fiber, let's say of about a few meters, so it can fit quite nicely on an optical table. So that's what we do in Salnoir 2. It's been done for years now, and so with many improvements over the years, but we have here in the middle the 2.5 hollow core fiber we're using, but we have main issues with that. First, we need to come into the fiber in vacuum first, because we have 10 millijoules coming out of the double CPA, and if we just propagate it through air, it will collapse by self-focusing. And so we need to feed the fiber quite tightly, because the beam is quite small, it's 500 microns approximately. And so it means that you just need to be perfectly on the core, because if you just get off, you completely burn the fiber, and it's well, 15K, I guess, something like that. So you just don't want to destroy the fiber. So we fill the gas with the output chamber there, and so we have a pressure gradient inside the fiber. Because as you can see, well, we need beam stabilization to be sure that we go through the fiber. And we have especially the two mirrors on the left and on the right, just before and after the fiber, which need to handle a huge amount of fluence, and then that can break quite easily. And every now and then we need to replace them. So there are kind of critical points there. So now we know how to do that, but it's always a little bit tricky. But anyway, that way we can produce 3.4 femtosecond pulses. That is a little bit more than one cycle. One cycle is 2.6 femtosecond for the TISAP systems, and with 3.5 millijoule on target. And so with that, we can reach the terawatt level on the target. But we could think about other configurations to, broaden the spectrum, and while keeping the spatial effects rather low. The first thing would be to use very thin plates and to put several of them through beam propagation. But there are many drawbacks for that. First, that if you put a plate, you change the beam propagation. You have a focusing effect anyway. So the caustic is changing, and if you do that with several plates, you can have like a chain reaction. If the energy is changing a little bit, well, you have the beam just going everywhere, and the beam waste and beam divergence goes crazy. And so this is quite tricky. So you need to have a very low number of plates, and to be sure that nothing will move. That's a bit complicated. So people do that, but that's still a little bit tricky. Or what you could do is to get an imaging configuration. That is, for instance, here we have one pattern with a beam which is focusing and diverging, and you just put two plates at the same distance from the waist. So the beam will have the same size on the plates, but with opposite radius of curvatures. And it appears that with this focusing first and then diverging beam, you can partially compensate for the spatial effects. And then with just one pass, the spatial effects canceled out, but you still have a broadening effect in both plates. And so you repeat that pattern as many times as you want. But once again, it's a little bit complicated system. So the best thing is actually to fold this repeated system into what we call a multipass cell, which is simply a Harriot cell, for those who know that. It's just two curved mirrors and a geometrical arrangement such that the beam can go back and forth inside the cell. So it's not a cavity, but it's close to it, and make several round trips inside it. And you just have to put an injection mirror and a pickup mirrors to get the beam in and out. So the beam never comes back to its original position, so it's not a cavity, but it's just like it. And then you put the plates at this position, and each ray you can see here is one pattern you see on the left. So it means that you have the waist at the middle of the cell and pretty large beams on the mirrors. So you can avoid damage on the mirrors. And at the waist, you have the highest fluence, but it's in vacuum for plates, for instance. But even you could replace the plates and put some gas. And so it means that it's very, very close to the hollow core fiber system, actually. It's almost the same thing. But it's much more convenient because all the high fluences, we talked about especially about the hollow core fiber, are actually disappeared. Because by design, the cavity can handle high fluences. And except that, we have no risk of damaging anything, especially the pickup mirror, the output mirror. We have almost no constraints, provided that the cavity can handle that. So no in-coupling chambers, no out-coupling chambers, no mirror damages, and no self-focusing. So that's very great. So actually, at the input, the beam is quite large already. So we have very little effects that we want to avoid, especially for hollow core fibers. So it's much more convenient. And so, well, this is how it works. So you can see on the movies that we can see all the beams going, making circles on the end mirrors. And here we have a configuration with 18 passes. So many people did that, but especially with ytterbium-based laser systems. So they start from several hundreds of femtoseconds and even the picosecond, so they definitely want to go shorter. But they only reach at maximum the few tens of femtosecond regime in one single stage. If they want to go to the few cycle, they need two different stages. And so that's what we propose, is to do that with the TISAF system, because we already start with few tens of femtoseconds, and we can go down to the few cycle regime in one single state, in one single step. So there were people doing this just before us, but with kind of moderate energies and rather long pulses of 8 femtoseconds. And we did that at the millijoule level, in so one single stage, and we can be proud of us because the LOA is the first lab to demonstrate TISAF post-compression at the millijoule level. Milestone. So this is the experimental setup. We have 1 millijoule, 30 femtosecond, 1 kilohertz. It's exactly the same front end as the one in Salle Noire 2. So here in Salle Noire 3. And we just first filter the beam to get very nice Gaussian beam to send it to the multipass cell, because we have to get the right size at the right position inside the cell such the beam is stable. It's a little bit tricky, but once it's done, everything works well. So it was the first time we were using a multipass cell, so we just wanted to be on the safe side for this. And we make several round trips, up to 18 passes, so it corresponds to more than 50 meter propagation length. That's quite huge. But the footprint is only 3 meters. So it's comparable to the hollow core fiber, which is 2.5 in Salle Noire 2. It's the exact same footprint. And then, in the end, we have chirp mirrors to recompress the broadened spectrum, wedges to finely tune dispersion, and in the end, we characterize the pulses with a frog, and also the beam with an imaging spectrometer to look at the spatio-temporal couplings. So with increasing gas pressure, we increase the nonlinear level, so the beam integral. So we start from the 0 millibar, which is just the fundamental spectrum, and then by increasing the pressure, we get broader and broader spectrum. But at some point, we completely destroy the spectrum. This is a limit we already know. And so we cannot broaden the spectrum as much as we want, so that's why we need to stop before. And if we plot the spectral width with respect to the gas pressure and also the FTL pulse duration, so perfectly compressed pulse, it's a utopia, but just to get an idea. We can see that first the spectrum is increasingly broadening and quite linearly, but then saturates. And it's because of dispersion. We have higher pressure, broader spectrum, and long propagation length. So the pulse gets linearly chirped, and so the intensity drops, and the cell phase modulation is less and less efficient. And so we can push it harder and harder, but at some point we get that tipping point where everything goes crazy. So we have to stop before to be sure that we can get a nice pulse in the end. And so that's what we did. we set to 16 passes to improve a little bit the efficiency. So 450 millibar of argon. And in the end, we get out with 5.3 femtoseconds for width of maximum, which is almost exactly 2 cycles. So we start from 30 femtoseconds and go down to 2 cycles, which is kind of nice. So the overall MPC transmission is about 80%. We have the compressor in the end of 86% efficiency. And so the overall efficiency for the post-compression is about 66%, which is quite huge because for the hollow core fiber, for instance, just the throughput and the broadening without the compressor included is about 50%. So even if we add the compressor, then we have a little bit higher efficiency of the compressor, but anyway, it's much higher than what we have in Séminaire 2, but with the same footprint and much less complexity. We can also look at the beam quality, so we can see here with the imaging spectrometer the spectral content with respect to the position in the beam. And we also can derive what we call an homogeneity parameter, with a V parameter, which is represented in red. So first, we can see that the beam is very nice. It's close to a Gaussian beam. And also the homogeneity factor is more than 99% correlation at full width at maximum and 95 at 1 over E square. So it means that all over the pulse, the spectrum is constant. And with such high B integrals, they're going down to 2 cycles, it's almost impossible to get such nice beams with regular post-compression experiment in free space. I mean, if just multi-plate setup, it's impossible. So the imaging configuration and the MPC really allows to get rid of the spatial effects. So just a quick summary. Yes, indeed, we have high efficiencies, 2 cycles, high beam quality, low complexity. Wow, that's pretty cool. But we are always limited by what we call the self-steepening. This is an effect closely related to self-phase modulation, which causes pulse breakdown. But we have that with hollow core fiber already, so it's not surprising. And also dispersion that we don't have with the fiber, with the hollow core fiber, because it's 2.5 meters only, and the equivalent length for the MPC is more than 50 meters. So that's why we experience dispersion, and that's what prevents us to go to the single cycle regime. We had 2, but we could not go with shorter pulses, unfortunately. And so we can try to scale a little bit the energy, because we started with 1 millijoule, we should do that with 10 millijoule for Séminaire 2. So we can test other things like divided pulse post-compression. We split the pulses in different replica, we send them to the MPC, and then we combine them to scale the energy. But also what we need is to manage the dispersion inside the cavity to be sure that the beam is not, the pulse is not getting chirped, linearly chirped, and the intensity won't drop, and so we can preserve a constant self-phase modulation effect all over the propagation. Okay. Yeah? We do that. Indeed, we do compensate the linear chirp that is coming from the gas pressure itself, just propagation. But I mean, to get a compressed pulse, that's necessary, yeah, for sure. But the thing is that we want to keep the pulse with the original shape first. So it comes Fourier transform limited, and then it needs to propagate while preserving its shape and its intensity, especially. But if you have a chirp, a linear chirp coming from the gas, the pulse will just decrease in intensity, and so the SPM effects will get lower. And so it means that we can compensate that chirp, but inside the cavity, or as it could be for very, very long hollow core fiber, what happens is that we try to get nice spectral broadening, but then the pulse gets chirped, and the let's say the broadening per meter is lower and lower and lower, and then saturates, and then you cannot get more. They want to do that. And we want to do that. This is the next step. Yeah, we were in collaboration with them, with the laboratory Charles Fabry and CEA. And we're thinking about that. But yeah, totally. Yeah, I don't think it's expensive, but the thing is that it works only with a specific pressure. Because you increase the pressure, you increase dispersion. So you need to know very well in which condition you will operate the MPC and just be sure of what you're ordering. I don't think it's very expensive, but I guess maybe we would need to order a set of sharpeners with several values to be sure that, oh my God, no, it's not working, so just replace it with another one and so on. And then in that case, we will get very, very close to the hollow core fiber situation with no dispersion. Yeah, and we could go down to the single cycle region. Yeah, that's the ultimate goal. For Gaussian beam propagation, actually not. It's a kind of, you can take that like a mode. And so a ray that crosses the middle of the beam is not parallel to the optical axis. It just crosses that way, but not necessarily with zero angle. So in the next DZ, it will be somewhere else. You see, you have the optical axis, and you have a beam crossing at the middle of the beam, but at the next step, it will be somewhere else. And you see, it's not collimated beams, rays. I mean, it's just a mixing of lots of rays, which are not necessarily parallel to the optical axis. So if you consider that, yes, the central beam is parallel to the optical axis, it doesn't work. But it's not the case. Actually, it's rays that are defocusing or focusing, and they almost have no zero angle with the optical axis. So that's why just few centimeters away, the configuration, the distribution of the rays has changed. It's the Gaussian beam propagation in terms of mode that tells you that. So that's why. So if you have a thick, very thick plates, it doesn't work because it's very short propagation length. So indeed, the rays don't get off really quickly, but if you just have thin plates, let the beam propagate and put another plate far away, yeah, this leads to kind of mixing the things. But I can show you some simulation afterwards if you want. I have some things that could help you to understand that. Because we have another topic already, and well, I need to get ready. So thank you for the question. So I'm not late because of me, but because of you. So I'm just going to go quickly because we said, okay, we have something that can just blur the spatial effects, but we have many other experiments that will take benefit of this. So the thing is that where could we put a multipass cell in the experiment in Vanuatu? So there or there or there. So what's going on? We need a nonlinear process. We know that the multipass cell can be adapted to any kind of nonlinear process, not only post-compression, but other things. And so we thought about the temporal contrast cleaving that we have in Vanuatu and that we also can find in Saljon. So as most of you know, the main pulse is never alone. We have many other things all around, especially the pre-pulse, which are the experiment killer. So we just want to remove them while keeping the main pulse as intense as possible. So it depends, of course, of the experiment, but we need a high contrast between the main pulse and the bottom noise floor. And so how do we do that? We just go through a nonlinear medium which plays with polarization this time. So the thing is that we want to just project the main pulse, which is the most intense, on the cross polarization while keeping all the garbage all around, which have much lower intensity, on the original polarization. And then we just filter that with a polarizer. So of course it's never perfect like this. It depends on the quality of the polarizer, but what we want to do is to favorize the main pulse projection on the cross polarization. And so we have several ways to do so. So we need to just look at the Kerr effect first with two polarizations. So this is self-phase modulation. We can see, so the evolution of the polarization A will be like this. Well, you can solve that by seeing, okay, it's just an exponential differential equation. So it's the beam, the electric field is just itself, but modulated with a phase which is proportional to the intensity. Okay, so we've said that already. But if you play with A and B, you need to make all the combinations between all the terms A, B, A star, B star. So with just one star, because it's a Kerr effect, so just one star, but we need to sort them out. First, we have self-phase modulation we can recognize. Here we have what we call cross-phase modulation, because we can see that it's still proportional to A, but now the modulations comes from B and not from A. So that's why it's cross, from the cross polarization phase modulation. And then here it's a cross-polarized wave generation. You can see that it does not depend on A. So if A is 0, this process can occur. And so you can have an energy transfer from B to A directly. And this is the cross-polarized wave generation. And in between, you have the cross-phase modulation from the X to W, so the exact spin, W things, you know. So it's just garbage we won't talk about at all today. But the thing is that for the two midterms, you have, midterms, oh my God. We have, they occur only with an elliptical polarization, because with A and B in phase, it's just a 45-degree polarization. You just rotate the basis and you get back to the original situation. So you need B and A being detuned in phase, and so that's the only solution for it to occur. And here, for the two last terms, we need a nonlinear anisotropy. That's a bit complicated, but let's say that it's like birefringence in the linear regime. Here we have kind of an anisotropic chi3 for certain crystals. So not all crystals do that, and you need to choose the right one, but it's possible to get this situation. And so you have the exact same thing with B, and you need to solve the equations between the two, highly coupled equations, but we won't do that today. So we're just going to talk about cross-phase modulation because it's straightforward from the previous experiment of post-compression we've been doing. How it goes? Well, just we select the terms here. We don't care. We removed all the prefactors just for clarity. And what happens when an elliptical polarization goes through a nonlinear medium? Well, it rotates. So we have degenerate cases with the linear and circular polarization. The circular is just going around, but nothing really happens. But with elliptical polarization, it rotates. And it rotates faster with higher ellipticities. And so the deal would be to make the elliptical polarization rotate by exactly 90 degrees, such that we can extract it. But as I told you before, only the highest intensity would rotate, because only the highest intensity will experience the nonlinear effects, but the low intensity would just not rotate and stay as they are, and so will not be coupled to the cross polarization. So this is the typical thing we do. We start with linear polarization, create an ellipticity, go through just an SPM medium, classical SPM medium, and with this ellipticity, it will rotate automatically. And with the right amount of nonlinearity, we get the cross-polarized ellipticity. Then with a quarter wave plate, we get back the linear polarization, and we polarize. So just you see. Now, I mean, it's quite simple because we just need quarter wave plates compared to and a polarizer compared to the previous experiments. Because otherwise, we still have SPM. You see, the SPM coefficients are still there, and we have spectral broadening. So, well, we take the original setup. We just remove that because now we know how to align a multi-part cell. And we add quarter wave plates, which are crossed, and half wave plates to tune the ellipticity, and polarizer in the end. And also a third order autocorrelator to measure the contrast. So we can see the spectral broadening occurring with increasing pressure, but we can also see the increasing throughput. Because first, when it's not nonlinear, when it's linear, the polarization and the polarizer are crossed. But then when the ellipticity rotates, we get higher and higher energies. So we can see that we can optimize a little bit to be sure that we are at the highest pressure possible to get the highest broadening, and to be at the top of that curve. And so that's what we did. I'm going to just throw that away. And in the end, we obtained 6.4 femtosecond. So it's a little bit longer than what we had with just the MPC alone with linear polarization. But I don't think we can tweak it a little bit more. But still, it's few cycles. It's a little bit more than 2 cycles. And we get, so the throughput of the MPC was a little bit lower than before, 73 instead of 80, so we don't really understand why, maybe pollution on the mirrors. But anyway, we have what we call the internal efficiency of 63%. That means that the NER on the cross-polarization is 63% of the overall signal that goes out of the MPC. And in the end, the global efficiency with NER and MPC throughput is a little bit less than 50%. And if you need to compress that, well, you have 40%. Every time we lose some energy. But it means that we get rather nice efficiency. 40% is comparable to what we have in San Martin with the hollow core fiber, but now with a high contrast. I mean, I hope so. So, but still, so it's definitely worth it. But the same drawback is the pulse duration is not single cycle. It's always few cycles. So yeah, we gain 3 orders of magnitude in terms of pulse contrast, definitely. And it's mainly limited by the polarizer itself. Otherwise, it could be almost perfect. Because all of this should not rotate at all, so we should get infinite, minus infinite, which is not a real situation, of course. Nice beam qualities as well, so I'm going to go quickly with that. But, well, it's the MPC, it's inherent in the MPC, so we get approximately the same results in terms of homogeneity. And then just a few words about the XPW, because we have that in Salle Noire too, but also in Salle Jaune. And this is a bit different because we have 2 separate polarization. You start with the A, just a single linear polarization, and 0 with B. And it means that the first A will just experience self-phase modulation, and B will just get all the energy from A directly. It does not exist at the beginning, but it gets the energy from A, and with different shape, especially because it depends on A squared A. So if you just tweak a little bit the formulas, you can see that the B pulse, which is generated, is much shorter than A itself, just at the very beginning. Of course, when B exists, you need to solve this couple equation, and you can see that you can go back and forth and distribute the energy between A and B as much as you want. Of course, it's for a monochromatic plane wave, so it's still a utopia. And if we do that with time and space, oof, the maximum efficiency drops a lot. And if you look at the beam profile and the beam homogeneity, it's just awful. So it's just like any kind of plate setup. If you do that, you just destroy the beam, and for the highest efficiency, you cannot use the beam anymore. And so let's use a multipass cell. So here is the Salle Noire 2 experiment. We have 2 plates separated, so to improve a little bit the efficiency, but it's quite difficult. It's very sensitive, but we still have a little bit larger spectrum, shorter pulses, but very low efficiency. Oh, the cross is not in the right place, but off, completely off. In my computer too, yeah. So you can imagine that this is on the 30% scale, okay? There. So it means we're far from the maximum, but we cannot do more because otherwise we destroy the beam and we have to stop with that. And even in that situation, we need a high beam quality at the input, and the output is always a little bit distorted and especially has some couplings. So let's put that in a multipass cell. Once again, it's the advertisement for the multipass cell. We can just remove the gas and put XPW crystals in the multipass cell, just like a plate setup for multipass cells. So it's in vacuum now, and we do the exact same experiment as before. We just have a polarizer at the output. So we add losses, of course, because these plates always have some losses, especially at the interfaces. So it's a little bit more lossy, but still it works pretty well. And the half-wave plate, of course. And here are the results. We can get very nice pulses, actually nearly Fourier transform limited, 15 femtosecond in that case, and with an internal conversion efficiency of 57% instead of the 30% we have in Séminaire 2. And the global efficiency is 30% instead of 20. But we have also very nice beam qualities and very nice contrast enhancement. We did that, we played also with the input spectral phase, and we could see that we could even increase the efficiency to 35% and internally 65%. We're just playing with the input chirp, and we could get a little bit longer pulses, but anyway, much more efficient. So we can even play to change a little bit the configuration, because once again, A and B are not correlated with the cross-phase modulation. For instance, is the same pulse with the elliptical polarization. Here it's just A and B, and they are completely independent, and you can treat them as you want. So you can really play with that, and it's kind of fun. And so once again, it's a different curve, I promise. This is not the same, but this is the exact same results. So I'm going to once again go through this. It's the same polarizer, so that's why it's the same curve. Not the same, but close to it. Once again, very nice beam qualities, really, really, really nice qualities this time. And so Gaussian profiles and high efficient homogeneity. Well, it's okay, just to see what's the pros and cons of those. Both, yeah, this is the MPC feature, high homogeneity, high beam quality, high global efficiency for the cross-polarized cross-phase modulation, but low global efficiency because of the plates, very, very lossy. So it needs to be improved. High projection efficiency compared to just bulky systems, so thanks to the MPC, of course. We can do few cycle pulses with the cross-phase modulation, but not with the XPW for now. But we are working on this. We can tune the broadening with the XPW, which is not possible with the XPM. So with the XPW, if you don't want huge spectra and use dielectric mirrors that can handle much shorter bandwidth, well, you can do that. If you don't want the spectrum, go for an XPW, not for the XPM, let's say. Well, the XPM will limit it by the pulse breakdown and dispersion, whereas with XPW, it's only dispersion you need to manage. We have no pulse breakdown because, once again, the two pulses are different. And so one will experience breakdown, the other one will go really fine. So it depends on what you want to do, but you can play with this. And what we want is a single cycle eventually. And it's going to be, I think, much easier with the XPW, just with the dispersion management. And we could do that with the cross-phase modulation, but we will experience ionization inside the cavity at the waist, and it's going to be much tougher to handle. So, sorry for this very long talk, but there were many, many, many results we wanted to show you. They are all related to the same thing, so I'm really happy to show them to you. Antoine is not there, so but they're here. And I would like to thank Laboratoire Charles Fabry NCA for their help. Also Jasmine and Zhao, who worked a lot to get those results, and the whole group, of course, and I thank you for your attention.